Hello everyone, welcome to lecture 34 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on nanofabrication. So in this lecture we will see the mostly used nanofabrication methods, and we will discuss about thin films and different ways of making thin films like physical methods, chemical methods and epitaxy, and then we will conclude this lecture. So this particular module will give you a brief overview of how different fabrication methods can help you realize the structures that we have studied in this particular course. So it will not be a very extensive overview or in detail study of the different fabrication methods. I will try to catch and touch upon different topics so that you have basic idea of how to realize the structures that we have discussed. So when we talk about nanofabrication lacks a clear definition, and it is not very distinctly separated from the term microfabrication. So new methods are constantly developed to make electronic components smaller, starting from micrometers to nanometers, and the same techniques can also be used for nanophotonics, plasmonics and metamaterials. So microfabrication, that those are typically done for larger parts, will become nanofabrication when the parts shrink and the dimensions become almost comparable to nanometers. Okay, so the basics remain similar. Now integrated circuit production drives this particular technology, and they provide extra advantages in the areas like photonics. Tools and techniques keep evolving with time. There is a constant research and updation going on to make the process more robust, so that there are less fabrication error and the yield increases, and there are also challenges coming from continuous shrinking of the component sizes. So the process has resulted in smaller and smaller electronic parts with widespread benefits. That is why you see all these devices, they are becoming very lightweight and small, compact these days. So that is because of the advancement in nanotechnology that allows the scientists and engineers to fabricate structures which are really small. Now if you look into nanofabrication, there are mainly three parts: thin films, lithography and etching. So thin films, as you can see, there will be a substrate and you can develop a thin film on top of that. This film thickness can be typically few to several nanometers, okay, or even micrometers. Okay, those are thin films. Then you have lithography. Lithography is basically a process of making patterns. Okay, so you can see it starts with a silicon substrate which is coated with a photo or e-beam resist. We will come into the details of this in the next lecture, but let us quickly go through what it looks like. Then you will basically have a hard or soft mask which actually got the pattern that you want to develop, and then when you expose UV or electron beam, okay, your photoresist, okay, if they are positive photoresist, they get developed, okay, and then they can be etched away by some kind of solvent, and this is the pattern of the resist that remains. Okay, so after that you can evaporate material, and that material fills in this particular gap, and then when you remove this photoresist completely, these are the patterns which are basically developed on the silicon. So you can, this is done by putting this in a lift off solvent. So all these are the standard processes in nanofabrication technology. So we will look into this in the next lecture. Today we will be mainly covering thin films, and in the last lecture of this module we will be covering etching. Okay, so here you can see that you have got a circuit material that needs to be etched, and you develop a photoresist first on that, okay, and then you can expose these areas of the circuit material to the etchant, they can etch away those circuit material, and this is what you get after etching. So, these are the three methods that actually help you develop those structures that you have seen in this particular course. Okay. So, these, as you can see, these methods are very much standardized and optimized for semiconductor industry, and that is where people are actually aiming towards making photonics material CMOS compatible, so that the same foundry with some minor modification can help us fabricate those nanophotonic structures or plasmonic structures. If we are going for totally different materials, that might be difficult for mass production at this current stage when the foundry is not supporting those kind of material fabrication. So, if you look into the thin film industry, thin film science is basically a broad field which is used in various industries. Okay, and thin films are ultra thin layers that can be found in products such as eyeglasses, okay, screens and vehicles. And these serve different kind of purposes, something like reducing reflection, preventing damage and altering properties. In tiny computer parts, these thin films can control electricity and help you switch. Okay. So, another important application you can think of is the gate dielectric in transistors, which is often less than 10 nanometer thick. So, those are also thin films. So, here you can see applications of thin film in different disciplines. So, if you think of optics, it can give you anti-reflection coating, highly reflected coating, something like laser mirrors, you can have interference filters, beam splitter, then thin film polarizers, integrated optics and so on. If you think of optoelectronics, you can use them for photodetectors, image transmission, optical memories, LCD, TFTs and all this. If you think of electronics, they can be like passive thin film elements like resistors, condensers and interconnects. You can think of active thin film elements like transistors and diodes, okay, and integrated circuits like VLSI circuits, they also use a lot of thin films. Then CCD, charge coupled device. You can think of chemistry where catalysis, electrocatalysis, biocatalysis, photocatalysis, all those things are the application. You can think of sensors, you can think of magnetic applications, engineering and processing, and also new materials. I will not read out all of them, but you can always see that there are a lot of applications of thin films. They are also very useful in biomedicine, where you can have neurological sensors, you can have claddings for depot pharmacy and biocompatible implant coatings. So, all these things are possible. So, there are vast application of thin film technology, not only in the area of semiconductor or photonics, they can actually have applications in lot more other disciplines. Okay, they can be used for alternative energy or green energy, something like in solar collectors or solar cells and so on. Okay, so as I mentioned earlier, these thin films can be really thin, and they can be from 10 to 1000 nanometers. So, typically 10 nanometer to 1 micron, that is what we call them as thin films. Okay, and these are for visible and infrared light, and for extreme UV light the films will become even more thinner, because extreme UV light has got a very short wavelength, and in that case you can actually use thin films of 1 to 2 nanometer thickness, and these are typically used in photomasks. We will come into this. So, right now just keep this new terms in mind. We will discuss about these new terms soon in this lecture or in the subsequent lectures. Now, thin film properties change based on how they are made. So, the key properties include how well they coat the surfaces, their density and their electrical behavior. And density affects how light bends in the film, and stress can wrap or crack it. So, this is the effect of density. When the thin films are made from compounds, the films makeup can vary depending on how it is created, and for single element thin films it is not usually of a worry. And when you develop thin films, the impurities, grain size and how tightly the elements or the particles are packed, they also affect how well the thin film will conduct electricity. So, their conductivity depends on all these parameters. Now, how do you make thin films? So, the process of making thin films can be broadly classified into two categories: physical methods and chemical methods. Physical methods involve transferring the material from the source to the substrate without changing its chemical state. So, it is a physical method. While on the other hand, when you think of chemical method, the film is basically created as a byproduct of some chemical reaction. So, let us look into the physical methods first. So, when you talk about physical methods, there are two widely used methods for adding thin films. One is evaporation, another is sputtering. So, these methods work like a special kind of painting with the vaporized material, adding tiny particles to a particular substrate. That will be the surface that you will be coating with the thin material. Evaporation and sputtering are part of a group called physical vapor deposition or PVD. In PVD, the materials are transformed into vapor and then layered onto a surface one atom at a time, and these processes are often carried out in high vacuum chambers that prevent interference from gases in the surrounding. So, if we look into the evaporation method involves heating the source material a lot until it turns into vapor, and vapor pressure plays a very important role here, because all materials evaporate at specific temperatures, as you can see here. So, this is basically the pressure, it is given in millibar, this one is in torr, and this is the temperature scale. Okay. So, that is in centigrade and that is in Kelvin. Okay. So, and here are the materials like tungsten, gold, magnesium, there are many more all listed here. Okay. So, this is basically a vapor pressure versus temperature curve for different kind of metals. So, commonly used materials barely evaporate at room temperature, right. So, you can see that gold with a very low vapor pressure below 10 to the minus 15 torr at room temperature. Okay. Now, when you see how the vapor pressure for gold is changing, okay, with temperature, so you can see that at 1500 degree centigrade it actually changes to 100 millitorr. Okay. And the vapor pressure also depends on the position in the vapor stream. So, the pressure decreases as the vapor moves away from the source. Makes sense? So, the closest it is to the source, it will be the highest vapor pressure. So, vapor pressure on the surface where the film forms can be estimated from the vapor flow patterns. And to calculate the film growth rate, pressure connects to the rate of atoms hitting the surface. So, that way you can calculate the rate at which your thin film will be growing. Often, instead of directly measuring the temperature and vapor pressure, deposition rate is controlled by adjusting the power to the source. So, that is also another method to adjust how much the temperature, how much thickness will be deposited. So, among the two methods of evaporation, you can see here one method is called resistively heating evaporation process. So, in this particular process there are two methods. So, this is the one, the other one will show in the next slide. So, in this one the pellet of the source material, that is here, it is actually put in a metal container like a boat, okay, and it is heated using a strong electric current around 100 amperes. So, this is particularly called resistively heated evaporation. So, it is very simple, needing only a low voltage DC source, but it has got some drawbacks. Drawback something like it is inefficient and there are chances of potential contamination due to other parts also getting heated up and evaporating along with the source. So, this both material or other parts also may get heated up and they will also vaporize along with the source material. So, this is how it works. The source material or evaporation material is here, the filament or the heater element is here. So, it hits this one up, the vaporized material particles they actually go and settle down on the substrate which is kept right on top of it, and this is done in a vacuum chamber. The second method is called a electron beam heating, okay, where the heated electrons are basically accelerated by high voltage. So, here you see the amount of voltage requirement goes very high, it is around 10 kilovolt, and then it is focused, this particular electron beam is focused onto the source palette. So, this happens again inside a vacuum. So, the electrons can be controlled by magnetic field, okay, and without hitting the gas molecules. This particular method of electron beam evaporation is pretty efficient, and here accurately heating of the source can be obtained so that it minimizes the contamination, and therefore it is a good process of developing high quality thin films, but only problem is that it requires a complex high voltage power source, and safety also becomes important here because you are dealing with very high voltage. Now, despite this, electron beam evaporation is widely used in thin film research and development. The reason you get a very high quality film. Now, the next method of developing thin film is called sputtering. So, sputtering also uses a vacuum system with an excited gas plasma. Okay. So, this is the typical setup for sputtering. So, here you can see that there is a gas inlet, this is the outlet, and the sputtering gas comes in and it hits the cathode sputtering target. Okay. So, that knocks out the metallic particles or atoms, and they actually go and settle down on the substrate forming a thin film. Okay. So, here you can see how it works. So, plasma ions, so these are the plasma ions which are, so this is plasma and then the sputtering gas enters, and the plasma ions are basically directed at the cathode, and they could knock the neutral atoms off the surfaces. You can see here M is the metal that has been knocked off, okay, and these atoms they collect on all surfaces including the substrate. So, you can see a thin film being growing on this, it is because of this. Okay. Now, in this particular method, unlike evaporation, it does not depend on heating. Okay. So, what is the method of atoms coming out? The atoms are basically ejected by momentum. So, this leads into much denser films. Okay. However, there are some benefits with sputtering because it is more flexible, and that is why it is popular in the industry compared to evaporation. Heating is not required, high voltage requirement is not there, so it is pretty good. Targets and plasma sources in sputtering can be made of different shapes for various coating setups, something like circles, rectangles, or any other unusual shape you can coat. Okay. Sputtering can happen upward, downward, or sideways, while evaporation happens only upward. Okay. So, these are the flexibilities with the sputtering technique. Moreover, the plasma power in the sputtering comes from a DC or RF source. Okay. So, for metal targets DC sputtering works, whereas for insulating targets RF sputtering is used, where the target acts as a capacitor for the plasma. We will not go into too much of detail, but it is good to know what are the different techniques being used for developing what kind of films. So RF excitation needs a matching network due to variable impedance, and it is used for both conductive and non-conductive targets. Okay. In sputtering, the atoms collide before reaching the substrate due to plasma gas, making it less directional than evaporation. So these are a couple of pros and cons of sputtering as compared to evaporation. There is a variation to it which is called reactive sputtering, and in reactive sputtering what happens, a bit of reactive gas like oxygen or nitrogen mixes with the argon gas to create compounds from ejected target molecule. Okay. So the setup looks like this. You have got a power supply here, this is the target which is kept, this is the plasma formation, you have got argon gas, and also you get some reactive gas, and this is the vacuum chamber. Okay. And from the target these are knocked off, and then the materials or nanoparticles which are ejected from this target gets reacted with this reacting gas, and then the compound gets deposited on the substrate. So during this process, as you can see, the atoms are ejected from the target by energized ions to form a plasma that is directed to the substrate under a high vacuum. Argon is commonly used as the sputtering gas, and the sputtering is carried out with DC power source and RF alternating current or ion assisted deposition. There are three methods. So mainly DC and RF sputtering are used, and in this particular case of reactive sputtering, a reactive gas such as oxygen are used for getting oxides. You can use nitrogen if you want to create thin films of nitrides. Okay. They are also passed to the reaction chamber along with the argon gas that you can see here, and these reactive gases react with the target atoms in the plasma to form the desired composition, and then they get deposited in the film, as I explained before. So while forming perovskite oxide films, multiple targets with different elements are simultaneously sputtered, which are reacted with oxygen, and they deposit as the desired film. Since the target elements and oxygen exhibit a large electronegativity difference, the formed ions can be negatively charged and they can be accelerated towards the substrate due to the difference in the potential of the negatively charged target and the grounded substrate. Okay. So the substrate is grounded. Okay. These ionic fluxes possibly act as sputtering ions to re-sputter the growing thin films onto the substrate, or modify the composition of the films, or etching the substrate. Okay. So the next method to develop thin film is pulsed laser deposition. So here the name itself tells you that you are going to use a laser pulse, okay, for depositing thin films. So how it works? So pulsed laser deposition, or PLD, employs brief powerful laser pulses which are as short as few nanoseconds to remove the target material. So you can see in the diagram here, you have got a laser pulse, you focus it and you hit the target, okay, and then there is a plasma plum that goes towards the substrate and it gets deposited. So the laser energy here is focused on the target surface, causing rapid material evaporation and atom injection. So that gives you this plasma plume, okay, and the atoms then they gather on the surface to give you that thin film. So what is the key advantage of this PLD? It can be performed in ultra high vacuum or with various pressures and gases due to the laser source being external to the vacuum chamber. So that is the flexibility it provides, and the main advantage of PLD is its ability to remove target materials in stoichiometric manner, that treating all atoms equally due to high laser fluence and rapid ablation. So, that way you are able to deposit uniform films using pulsed laser deposition. So, PLD is particularly suited for complex ceramic films like yttrium barium copper oxide YbCO, lead zirconate titanate PZT, and different other carbides, oxides, nitrides, okay, that are challenging to deposit using other methods. So, you can actually deposit this kind of films using PLD method. So, as I told you that the main advantage of PLD is that it is non-discriminatory, and it gives you stoichiometric removal of target atoms, okay, and it facilitates, and it comes from rapid ablation and high laser fluence. So, quickly this evaporation takes place, and it takes place from the entire target. So, that happens very quickly. So, with that we more or less cover all the basic methods in this particular physical methods of depositing thin films. Now, let us look into the chemical methods of depositing thin films. Now, as we mentioned before, that chemical methods will deposit the thin films as a byproduct of some chemical reaction. So, chemical methods, they offer uniform, well covered and stoichiometric films, but different gases and chambers are often required for each type of film. So, that makes it very specific. So and it is, that makes it also costly if you are experimenting in different films, because and using different gases. So, you need different chambers for different film types. So, the most common chemical method is chemical vapor deposition, where gas precursors enter a chamber and a high substrate temperature prompts a reaction to build the desired film. So, different types of CVDs are there. One is called low pressure CVD, you have atmospheric pressure CVD, you have plasma enhanced CVD, and atomic layer deposition. So, CVD requires low pressure and high substrate temperature that ensures that the reaction occurs only on the substrate's surface and not in the gas phase, which could lead to particle formation and surface deposition. So, here is the setup typically used for low pressure CVD. So, in this particular case of low pressure CVD, the reactor consists of a quartz tube that you see here. This is a quartz tube that is connected to a pump, okay, and the gas inlet is used to introduce the reactant gases, as well as the gases needs to purge the system. Typically nitrogen is used for purging, and the wafers are loaded through the door which is on the left. So, you can open this door and you can load this sample, okay. In low pressure system, the wafers can be placed closer, as you can see here. A furnace, so this is a 3-zone furnace that is there from the 3 sides, okay, top, back and bottom, okay, and this particular one actually encompasses the quartz tube, and this heats up the chamber, which drives the reaction rate faster. Now, what are the advantages of low pressure CVD? The first thing is it is a relatively simple design. So, excellent economy, it gives you high throughput and very good uniformity of the thin films. But there are some disadvantages also. So, you can say what are the disadvantages? They are susceptible to particle contamination. So, it requires frequent cleaning of this setup, and also you need to compensate for gas depletion effects. Next methods we will see is plasma enhanced CVD. Now, single wafer process chambers for plasma CVD look somewhat similar to this low power CVD, okay. Adjacent figure here, it shows a schematic that tells you how exactly single wafer plasma chamber will look like. So, as with the single wafer LPCVD chambers, here also the precursor gas is fed to the chamber using the shower head. Okay. So, you see here, and that ensure the uniformity of the precursor concentration over the wafer face. So, this is where the wafer is kept, and this is basically on a heated plate. Okay. So, the wafer sits on a heated plate and the byproduct gases are exhausted through this outlet which is below the wafer level. Okay. Now, with direct exposure RF PECVD systems typically employ shower head as an electrode for the introduction of the RF energy to create the plasma that you see here. Okay. The precursor entering the plasma undergoes electron molecule collisions, producing high energy excited molecules and molecular fragments that absorb on the substrate surface and deposit the film. So, these are the gas inlets. Okay. So, the next method is atomic layer deposition. So, atomic layer deposition or ALD, it starts by a pulse, okay, of metal organic precursor gas into a deposition chamber. As you can see here, this is the first stage. Under certain conditions, the gas will react with the surface species of the substrate in a self-limiting reaction that is terminated when the surface runs out of the reactants. So, that is why it is called self-limiting reaction, and the excess gas is purged in the next step with a neutral gas. So, as you can see here, nitrogen is being used for doing the purging. You can also use argon depending on the process requirements. So, the second reactant is then introduced into the chamber in the third stage. So, here the second one is introduced, and again that starts reacting with the surface species like that, and the excess reactant is again purged in the fourth step. So, that gives you one particular cycle, and then it is repeated. So, you can actually atomic layer deposition, as the name tells you, you can actually deposit layer by layer of atoms and grow your thin film. So, in an ideal ALD process, one atomic layer of material is deposited in each cycle. That is what it does. So, you can actually precisely control the thickness of the films using this particular method. The number of cycles will then determine the overall thickness of the film. Okay. And ALD deposited films are highly conformal, and they can be used for coating and encapsulating of complex geometries, because you have complete control on the thickness of the films that are being deposited. Okay. So, with that we move on to the third method of depositing thin films, that is epitaxy. So, when we talk about epitaxy, it basically, this word comes from a Greek word which means ordered upon. So, epitaxy means basically the growth of a single crystal film on top of a crystalline substrate. So, for most of the thin film application, which includes soft or hard coating, protective coating, optical coating, it has little importance. However, when you go for semiconductor thin film technology, this becomes very crucial. The crystalline growth becomes very crucial. So, this is what we mean by crystalline growth. So, this is not epitaxial, but this is epitaxial. Okay. So, it is a crystalline growth, ordered and crystalline growth. Now, note that when we talk about the other thin films, if they are not crystalline, they are typically amorphous. Okay. So, amorphous films are preferred over thin films due to their simpler production, okay, used when their properties can meet the application requirement. So, if you are able to provide a amorphous film that can serve your purpose, you stick to that. You do not need to develop a crystalline film or a very ordered film, because that makes it very expensive. Okay. Now, when we talk about the optical coatings, where the refractive index control is crucial, you actually use amorphous films. Okay, that works for you. Metal films are commonly used in amorphous form for consistent electrical conductivity and optical reflectivity. While amorphous materials, they lack distinct electronic band structure due to their randomness, crystals process defines band structure with their ordered arrangements, and crystallization can occur through annealing. Okay? But epitaxy is a more formal process for creating high quality crystalline films. So, here is an example of method of epitaxy, which is metal organic CVD. So, this is very similar to LPCVD that you have seen. It grows thin layers by sending special gases over the substrate. Now, if you see the shower head here, okay, in this particular figure, it is designed for equal distribution of gaseous precursors through the chamber onto the wafer. So, these are different gases which comes in. Okay. It allows a quick and uniform diffusion of gas molecules onto a rotating heated wafer. So, this is the wafer which is being on a rotating platform and which is also heated. So, nitrogen gas is typically used for purging the system, and argon gas can be used as the carrier of the metal organic precursors. These are the wafer loading window, this is the exhaust, okay, and this is where the resistance heater is that heats up the platform. Okay. So, you can actually see that this particular wafer rotates on this platform at a speed up to 1000 rpm. The film thickness, which is grown epitaxially, that means orderly, okay, is mainly controlled by deposition time and the growth rate. And growth rate is also strongly affected by the growth pressure in the chamber, substrate temperature and the precursor flow rate. So, these are the factors they actually decide what will be the growth rate of the film. The other method is called molecular beam epitaxy. This is an epitaxy method where thin film deposition of single crystals take place. So, in this particular method, it is widely used in manufacturing semiconductor devices, something like transistors, and it is considered as one of the fundamental tools for development of nanotechnology. So, MBE, molecular beam epitaxy, is used to fabricate diodes and MOSFETs. MOS means metal oxide semiconductor, FETs, okay, working at microwave frequencies, okay, and to manufacture the lasers used to read optical discs such as CD and DVDs. So, I will go into the process soon. So, remember that MBE is considered to be one of the cleanest, but also one of the most technically challenging and demanding process, because this MBE growth takes place in ultra high vacuum environment. So, this is the chamber which is a ultra high vacuum UHV chamber. So, an experimental setup, as you can see here, it consists of two or more Knudsen effusion cells, or you can say them as K cells, which are located at the bottom of this ultra high vacuum chamber, and they are aligned towards the center of the chamber like this, okay, where the sample holder with a substrate. So, this is the sample holder where the substrate is actually located. Now, each individual K cells, they contain different elements in ultra pure solid form. So, when we say ultra pure, the purity is typically 99.999%. Okay. So, what kind of materials like selenium, bismuth, okay, they are used in the thin film synthesis. Now, how it works? The process of MBE growth starts by heating these K cells to appropriate temperature until the elements in each cell reach a sublimation point. Okay. And Then the shutters over here, as you can see, these shutters, this is open shutter, and this is a closed shutter. So these shutters are then open, and the physical vapor from each K cell diffuses through the chamber until it reaches the substrate and get deposited, and this is how thin films are being formed. Now remember that for more uniform growth, substrate can be continuously rotated at low rotation speed. So when I say low rotation speed, it is typically 1 or 2 rpm, okay, by utilizing a stepper motor which can be attached to this magnetic manipulator. So this is how in this form it can be slowly rotated, and the electrons which come from this reed gun, okay. So this is electron diffraction gun. So you can see that it actually incident electron at a very low angle, and you can get the diffracted electron, and you can observe the pattern here, and this pattern can actually reveal the quality of the film that is being developed, and also you can measure the film thickness starting from single monolayer, okay. So as I told, this particular characterization is done by using reflection high energy electron diffraction, that is RHEED, okay. So in this particular method, the final composition of the film will depend on the temperature and the surface atomic structure of the substrate, as well as it will also depend on the flux ratio of individual components which are reaching the substrate. So this is how you can mix things up and get a thin film of a particular composite material. Selective opening of the structures, shutters of each K cell, they will ensure growth using only specific elements. So you can also do one by one kind of, just by opening the shutters, you can do one layer first and then the next layer and so on, and you can characterize the thin film that is getting generated by this reed method, okay. So this particular table sums up all the techniques that we have studied till now. So you can see the methods are being mentioned here. So evaporation, sputtering, pulsed laser deposition, low power CVD, plasma enhanced CVD, ALD, MOCVD and MBE, and you can see the parameters on which they are discussed. So you have substrate temperature, deposition energy, pressure, step coverage, defect density, uniformity, deposition rate, and the materials that are used and what are the different applications. So this actually gives you a very good idea, and what is important to see here, that all these methods more or less are very uniform, other than pulsed laser deposition that does not give a very good uniformity, and you can see that this is pulsed laser deposition is also slow, and these are first evaporation and sputtering are first deposition method. These are physical methods. In chemical methods, LPCVD and PECVD are first methods, okay. And you can also see the substrate temperature. In this case, you can have a wide range. In case of physical method, in LPCVD it should be high, PECVD it should be moderate, and these are the materials that can be used. So when you talk about MBE, these are typically compound semiconductors like gallium arsenide, indium phosphide and aluminum gallium arsenide. MOCVD, you can again use the similar kind of compound semiconductors. Atomic layer deposition is useful for alumina, hafnium oxide, silicon dioxide and certain metals, okay. Then silicon dioxide can be also deposited by low pressure CVD or plasma enhanced CVD, okay. Polysilicon can be done by PECVD, okay. Pulsed laser deposition can do complex compounds, as we mentioned, though it is poor or slow, but this method only allows to develop this kind of complex compounds like PZT, YBCO and other ferroelectric materials and so on. So these are the different applications. So optical thin films, as you can see, evaporation and sputtering, they are the most commonly used for making thin films that can be used for photonics application, okay. Then MOCVD, they can manufacture optoelectronic devices, and MBE, they are also in the useful for research and development in epitaxy and other optoelectronics components. So, this particular chart should actually give you a complete overview of the different processes in thin film growth and what are their pros and cons and what are their applications. So, with that I thank you for your attention, and we will stop here, and in the next lecture we will look into the methods of lithography and pattern transfer, of how to make a particular pattern on for your device. And if you have got any queries regarding this lecture, you can always drop an email to this email address mentioning MOOC on the subject line. Thank you.